Alright, so today we're going to look at bisectors of triangles and the line or points of concurrency and that are formed by bisectors of triangles, also made by medians and by altitudes. So some of our vocab words. So our warm-up, if x is, or we need to find x if the measure of angle A is equal to 10x plus 15. The measure of angle B is 8x minus 18. The measure of angle C equals 12x plus 3. So here's our triangle off to the right here. We know that two of the sides are 15, so that means the angles opposite of them are congruent. So that means that the measure of angle A is equal to the measure of angle C. So we can just plug in our expressions for those. 10x plus 15 equals 12x plus 3. Now subtract 12x from both sides. You get negative 2x plus 15 equal to 3. And then we subtract 15 from both sides. 3 minus 15 is negative 12. So negative 2x is equal to negative 12. We divide by negative 2. X is equal, negative divided by negative is positive, 12 divided by 2 is 6. Number 2 wants us to find y if it is equilateral and gives us a measure of one angle. So if the measure of one angle is 8y plus 4, they all are that, and since it's equilateral, all of the angles of the triangle are 60. So all we have to do is set 8y plus 4 equal to 60. Subtract 4 from both sides. 60 minus 4 is 56. We divide by 8 on both sides. And 56 divided by 8 is 7. So, our new vocab for today: perpendicular bisector, concurrent lines, point of concurrency, circumcenter, InCenter, median, centroid, altitude, orthocenter. So, all of these kind of go together. So, perpendicular bisectors come together to form the circumcenter. The angle bisectors, which is not one of our vocab words now, but it is one we've known already, angle bisectors come together to form the InCenter. Medians come together to form centroids. Altitudes come together to form orthocenters. So, here's the perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. And then the converse of that just flips it around. If a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So, we need to find BC here. C is on what looks like the perpendicular bisector. We know that because, first off, it is perpendicular at D. So that tells us it's perpendicular. And then we also have these little marks on either side showing that it is splitting it in half. And these tell us that it is the bisector. So it is the perpendicular bisector. You put those together. So since that is the perpendicular bisector, C is on the line with D, and that means that AC is congruent to BC. So AC is equal to BC, and that if AC is 8.5, that's equal to BC as well. Next we have the Circumcenter Theorem. So this is what I was talking about earlier. All the perpendicular bisectors of a triangle join together in the middle of the triangle, not the exact middle, but inside of the triangle to form what is known as the circumcenter. So the exact words here say the perpendicular bisectors of a triangle intersect at a point called the circumcenter that is equidistant from the vertices of the triangle. So, actually, before I move on, I forgot one other thing. There's also another thing that happens here. So there's a lot of congruence here because they are perpendicular bisectors. All the sides are being split in half exactly. Also, the points or the lines coming from what is the circumcenter, P, to the vertices are congruent. That's what that equidistant part means. So PC is congruent to PA and PB. And that's what it's saying in the example there. PB is equal to PA, which is equal to PC. So now our example here, a triangular shaped garden is shown. Can a fountain be placed in the circumcenter and still be inside of the triangle or inside of the garden? So all we need to do is graph out, since we don't really have any other means, we're going to just draw out about where our perpendicular bisectors are. So first thing I'm going to do is kind of figure out where I want my perpendicular bisectors to bisect, or as close to the middle as I can get them. So those are pretty close to where the bisectors will intersect, or where they will cross with the sides of the triangle. So now I'm going to draw my perpendicular bisectors. So I'm just going to start from these points I just drew and draw lines that are perpendicular to those lines. Now remember, perpendicular bisectors go both directions. And you got to make sure that you draw it long enough to intersect with the other perpendicular bisectors. So there's one of them. It's a little wonky on the bottom part, but that's okay. Here's my next one. So now we already have two intersecting, so the third one should intersect about that same point. If it doesn't, then we did something wrong. And that looks pretty good, actually. Okay, so it looks like our circumcenter is this point that's on the red box around the picture, which means it is not inside of the triangle. So the answer here is no. The circumcenter lies outside of the triangle. So now on to angle bisectors. So the angle bisector theorem says if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. The converse of that, if a point on the interior of an angle is equidistant from the sides of the angle, then it is on the bisector of the angle. So just like our first problem we had, here we have to find dB. And once again, we are given that these are bisecting, so this is our angle bisector because it does have this little pink arc on both of the angles that are being split by the ray AD. Because of that, from D to C is 5. That means that from D to B should also be 5. So dB is equal to DC, and we know DC is 5, so that means that dB is also 5. So, the InCenter Theorem. The angle bisectors of a triangle intersect at a point called the InCenter, that is equidistant from the sides of the triangle. So, similar to the circumcenter, the InCenter has some congruence going on here, mostly with angles. However, the lines coming from the InCenter to the sides of the triangle perpendicular to the triangle sides are congruent. So PE is congruent to PF and to PD. All of those are the same distance away. The main reason for this, by the way, is that the InCenter is where a circle inside of a triangle would be centered. This is the incenter. The circumcenter is the other way. The triangle is going to be inside of a circle. The center of that, or the center of the circle, is the circumcenter. So in center, the circle is in the triangle. The circumcenter, the circumference is around the triangle. Alright, so here's our example. This one here, we are given some sides of the triangle and we're given one of the angle bisectors. We also are given a couple angles, which are great, but we don't really have any means at this point in time to go from angle to side of a right triangle. So the angles are great, but they don't really help us. However, we have learned in past math classes, not in here just yet, what is known as the Pythagorean Theorem. So we're going to use Pythagorean Theorem, which, if you're unfamiliar with, is a squared plus b squared equal to c squared. So in our case, we're mainly going to focus on this triangle that has SU in it. And the reason we're going to focus on that triangle is because SU, ST, and SR are congruent, and we're looking for ST. So A and B can be either leg of the triangle. So 8 can be our A. B can be SU. And C would be the 10. 8 squared is 64. We're going to leave SU as SU. 10 squared is 100. And we subtract 64. And for SU, I'm going to write this on the side, SU is equal to SR is equal to ST, which is what we're trying to find. So 100 minus 64, we'll replace SU with ST. 100 minus 64 is 36. To get rid of a square, we're going to square root. We'll cancel the square root. So ST is equal to, square root of 36 is plus or minus 6. We're talking about the length, so it's just 6. Centroid theorem. So now we're looking at the combination of the medians of a triangle. So medians, by the way, if you don't remember from your vocab, are from one vertex of the triangle to the midpoint of the opposite side. So C is a vertex. The median goes from C to J, and J is the midpoint of the line AB, which means it splits it perfectly in half. Now, the congruence you can see is the only congruence involved here, but there is a ratio involved when it comes to the lengths of the altitudes compared to where the centroid is. So on BL, BP is equal to 2/3 of the entire thing, BL. So say BL was 6. Multiply that by 2/3, and we now know that BP would be 4, PL would be what's left over, the 2. So let's figure this out. We know that YV, this length here, is 12. We want to know what YP is and what PV is. So first off, we know that YP is the point from the section from the vertex to the centroid, which means YP is 2/3 of YV, and YV is 12. So we can multiply by 2, that's 24, and 24 divided by 3 is 8. So yp is 8. Now, for PV, we have some options. We can just do the 12, that the whole thing is, and subtract away the 8. Or we can know that PV is equal to 1/3, because there's 3/3 total. 2/3 were already used of the 12. Both of these will get us 4, and that is equal to PV. The orthocenter is our last point of concurrency. This one combines where the altitudes go together, and the altitudes are again going from a vertex, traveling to the opposite side, and instead of going to the midpoint, it goes perpendicular. So when you think of altitude, think of height, right? It's the direct distance from the vertex to the side, which means that it's going to end up being perpendicular to the base opposite of it. Now, the problem for this one is quite long. So what we need to do first is figure out the slopes of all of our lines for our triangle. Conveniently, we are given a graph, so that makes finding the slope a little easier. So for JH, we go rise, 1, run, 1, 2, 3, 4, 5, 6. So it's 1/6. For IH, we go up 1, 2, 3, 4, 5. To the right, 1, 2, 3, 4. So it's 5/4. And then from I to J, we go up 1, 2, 3, 4. We go to the left, so it's negative 1, 2. So negative 4/2 is negative 2. So now, we're going to sketch out where our altitudes should intersect. So remember, altitudes go from a vertex and then perpendicular to the side opposite the vertex. So even with just 2, we should be able to kind of see where it's going to be. But with all 3, it's right there in that point. So now that's saying that I'm exactly perpendicular. I know I'm not, and that's okay. So we're not going to just estimate what the number is here, though. It is definitely going to be a fraction. And again, we know that the altitudes are perpendicular, right? So this line here is perpendicular, this one's here, and this one here. So that means we can actually just put our focus on 2 of these, find the equation of the line for the altitude, which we know is going to go through the vertex, and then be perpendicular to the side opposite. So we have the slopes for those. So that means we have a point, we have a slope, we can find point and slope and find our equations. So first off though, since they are perpendicular, our slope is going to change a little bit. So we're not going to use the 5/4. That one's great, but we're not going to use it. 1/6 gets us a -6 for our slope, for our altitudes. Actually, let me write that in purple. Makes more sense. And then for the -2, it becomes positive 1/2. Those are much cleaner numbers to use for finding our point. I'm going to warn you now, though, the point is both the x and y coordinates of the point are pretty non-even numbers. They're pretty long decimals. So we're going to round on those, but that's for the end. So now we have our slopes. We have our m. Our point that we're going to use, x1, y1, for each one. One of them is going to be 1, 2, and one of them is going to be -3, -3. So for our first one, y minus y1, let's say it's -3, so y plus 3, equal to, the slope of that line is the -6, times x minus x1, which is also -3, so plus 3. So we need to distribute the -6, so y plus 3 is equal to -6 times x is -6x, Negative 6 times 3 is negative 18. We subtract 3 from both sides. And y is equal to negative 6x minus 21. That's one of our two equations. We need to do this one more time. This time for the point at h and our slope negative 1 half, or not negative, 1 half. So y minus y1 here is 2 equal to 1 half times x minus 1, or x1. Then I'm going to distribute the 1 half. I'm also going to change it to decimal in the process. So y minus 2 is equal to 0.5x minus 0.5. I'm going to add 2 to both sides. So y is equal to 0.5x plus 1.5. Now, we need to know where these two intersect at, which means we need to do a system of equations. Since they are both solved for y already, all we have to do is set them equal to each other. So, negative 6x minus 21 equal to 0.5x plus 1.5. This is going to get our x value out, and take that and plug it back in. So, first thing we're going to do is subtract 0.5x from both sides. Negative 6x minus 0.5x is negative 6.5x minus 21 equal to 1.5. We're going to add 21 to both sides. And negative 6.5x is equal to 22.5. We divide by negative 6.5. And x, so our x value, I'm going to write it all the way to the right, is equal to negative 3.46 if you round. Now we need to find our y value. To find that, we can plug this negative 3.46 back into either equation. So y is equal to negative 6 times negative 3.46 minus 21. And this all comes out to be about negative 0.23. So that means our final answer is our point at negative 3.46, negative 0.23. And if we look at what we graphed, it is pretty close to that. It needs to go out a little bit more to the left probably, and maybe up a little bit more on the y side, but that's not too bad. Pretty close. So, again, got worked on getting everybody into Google Classroom and on Socrative. Here's all of these together: the perpendicular bisector, angle bisector, median, altitude, and what they form when they go together. Perpendicular bisectors form the circumcenter, angle bisectors form the InCenter, medians form a centroid, altitudes form the orthocenter, and then what's special about them and an example. Here's your exit ticket.